Yes.
Yeah. So just uh, to have a remark in response to Mehdi's good question. Yes, given so the fact that we have homomorphisms is going to allow us to not only represent for any C set, the fact that Catlab allows us to compute homomorphism allows us not only to define category where we have objects being instances of a C set for a given category C, for the graph schema. Each of these will be graph, and the morphisms will be graph homomorphisms, these structure preserving mappings between them. But this further allows us to build up categorical constructions involving this, because these categorical constructions, things like when we have products, where we have coproducts. So product diagram here, coproduct diagram here, for example. These morphisms here are now, for example, graph homomorphisms. So each of these objects would be a graph, let's say, and this will be a projection of graphs from some graph that's a product of graph projecting down one graph, projecting down another, or from another graph projecting down to it. If we had an equalizer, each of these morphisms here in this category, we could have an equalizer shape within our C set category. Within this sort of category, for example, for graphs, we could have an equalizer shape, and that equalizer would, each of these morphisms would be a graph homomorphism. So this would be, one graph, this would be another graph, this would be another. And these graph homomorphisms, we could characterize the equalizer, this would be a monic arrow, as it always is. This is always an arrow that is kind of the flavor of being injective. It's not gonna take two vertices here and squish them down into one. No. It's gonna maybe like embed this in here. It's gonna be like E is a sub-object of this. E is a subgraph of this. So this graph, and this is maybe a subgraph, right? That's gonna be the subgraph. Capital E is gonna be the subgraph of X, such that F, the way F maps each of those vertices, and indeed edges, is the same as where G maps them. So this is going to be the subgraph of X that it's kind of mapped in the same way by F and G. But of course, this is nothing only about graphs. If we have a category of C sets of where these are stock flow diagrams, we can compute an equalizer for that, of causal loop diagrams, Petri nets. Each of these Petri nets, each of these are homomorphisms between Petri nets. And because that's a topos, we can take the equalizer of it, we could take the co-equalizer. And indeed, as we'll talk about, and as we'll briefly review, we can take the product and coproduct, etc. Okay, so the first of these operations, these categorical constructions, these universal constructions, these constructions which identify universal objects in our category, objects with kind of the best in terms of certain properties, like the best in terms of encapsulating information about two objects, A and B, about both of them simultaneously, about capturing information about either A or B, sort of side by side. Those are these are associated with these universal constructions, these ones that are the best in terms of having some universal property. Any other object which kind of is the pretender for the throne, has these abilities that this one does. This is the best one. It's the one through which all others factorize on their way from these here. They all go through this. There can be others that have a way of representing things from A and B side by side, but this is the best one in the sense that any other can be expressed in terms of this uniquely such that this can be used, right? And similarly for this. So we're going to be able to define these, and here we're going to treat with products, which is this sense of having sort of all the things of A and all the things of B, in combinations of them, and coproducts, where we have all the things of A and next to all the things of B. Products for sets, if we're in the category of fin set, the objects, so A and B here are finite sets, A times B is going to be, well, it's going to be all the elements of A times for every combination of all the elements of A and all the elements of B. Here we go. Right there. This is our product object. And any other object that can kind of enumerate those in A and enumerate all those in B here can be expressed in terms of this. Oh gosh, this shouldn't be. I'm sorry, this is just one example, but we could see this in general for any other, like if we had A cross B or something like that, that could factorize down, we could express it in terms of this, or A cross B slash 2, cross 2. We could express it in terms of this. Okay, so let's go see this in terms of Catlab code if we could. So we should open 9 prime, not 9 prime, products and coproduct graphs. Okay, here we go. We're going to see Catlab enact this idea, put it into action, realize it computationally. And we're going to see that, folks, together. Okay, so here we go. I'm going to take Catlab, and we're going to go and look at the graph schema again. We're familiar with that. And we're going to go through this quite quickly because it's really getting late, and I'm sure all of us value our, getting a full night of sleep before tomorrow's class. Okay. We're going to get a requisite category in which we're going to be working. It's going to be a CSET category of graphs. And we're going to take what's called the terminal object, which is a very particular type of universal construction. It is a limit, and it's going to be the terminal construction to which everything else has one arrow. And we saw it before. It's the degenerate. Remember this degenerate one with a single loop? That's what we have now. The apex of this is this very particular graph, which has a single vertex in a single loop on that vertex, a single edge, going from that vertex to itself. Every other one can be compressed down, can be squished down into that one. It may not be pretty, but it can be squished into it, and uniquely squished into it, right? It's kind of like a singleton set, that any other set can be sort of mapped to the singleton set without any choice in the matter, right? There's only one possible mapping from any other set. Can have hundreds of elements, and to go to a singleton with just a single thing in it, there's no choice in the matter, right? There's no choice in the matter here. There's a unique morphism. We could also look at the initial object, the graph that it's a graph we're dealing with that has a unique mapping to every other thing. Well, what is that? Well, it's the empty graph. It's the empty graph. Just like an empty set has a unique mapping to any other set, sort of a vacuous mapping, a mapping with nothing to do. Therefore, it's vacuously true that it exists, even to the empty set to empty set. Here we have the empty graph can be mapped to any other graph. Every edge, every vertex has to be mapped to some vertex. Well, there's no vertices. Every edge has to be mapped to an edge. There's no edges. It's just vacuously true. It's a single unique vacuous one to every other. Okay, now we can define some graphs. Okay, this is our familiar friend, GA. We're all enjoy the pleasure of acquaintance with that. Now we can define an end-to-end one. What my naming lacks in naming constructions lack in creativity of name, they make up for in number. Okay, so we're gonna define these end-to-end ones. We can define a unit graph. Oh my goodness, that's just the one we had earlier, right? Reciprocal pair. Hey, where's our? Oh no, we should have. Oh come on, we should have had a reciprocal pair. Come on, two graph is. Let's go look at our reciprocal pair. Oh, there it is. It's just a couple lines down. Maybe I stand corrected. I was panicking and I shouldn't. Okay, there we go. There we go, folks. Look at that. There's a reciprocal pair. There's a single vertex. We could ask, hey, what are the homomorphisms from the single vertex reciprocal pair? Well, we can say go compute. It's going to find two, right? One into there, one into there. Okay, connected pair. But we've seen enough with homomorphisms. Like that's not new. Let's go take the coproduct of these graphs. Let's take the coproduct of the single vertex, this guy here, and the connected pair, that one there. Hey, check it out. Check it out, folks. We're going to take the coproduct. Well, the coproduct is just like putting them next to each other, isn't it? It's just like, as John By said, it's just like taking two things like this. Oh, I wish I had a Tinker Toy set next to me. But it's just like it'll be like taking these two things, right, and just putting them right next to each other on a piece of paper. They're not articulated in any way. They're just stuck next to each other, just like that, right? They're just next to each other. But that's what a coproduct is. That's the flavor it has. And we could take a coproduct, a reciprocal pair, and connected pair, put them right next to each other, lay them out like cordwood. Okay, now let's do something different. Instead of taking, so we've been talking about taking the coproduct of these things next to each other. It is A or it is B, and your pick. There they are next to each other. These two, as it were, choices. Now we're going to take the product of two graphs. So we're going to take a product of this and this, and the nature of the product is the nature of the coproduct was very inclusive, right? It had the two things next to each other. They didn't interfere with each other in any way. Product, we've got to remember the notion of product here. I mean, like product was considering sort of combinations. But gosh, if one of these was empty, then we would have none of them, right? None of them. So when we take the product of graphs, we're going to get a graph out. So we have product of graph A and graph B. We're going to get a graph out that each of whose vertices is going to be a pair of a vertex of A and a vertex of B. Gosh. And there's going to be a morphism between, if we have in two vertices in graph A and A prime, and we have two vertices in graph B and B prime, there's going to be a link from the vertex A, comma B, because each vertex in the product of those two is going to be a pair of A vertex from A, a pair of vertex from B. So we're going to have so in our product graph, we're going to have a link in that product graph from AB to A prime B prime. If and only if this links from both A to A prime in graph A and from B to B prime in graph B. It needs both. If one of those edges in graph is missing in graph A or in graph B, we ain't going to have such an edge in the product graph of A and B. It needs both. And it's very constrictive. It's very demanding. It's very, got to have them in all. We're not going to give you any in the product and the result, right? I'm not going to have one in the result unless you have them in both. It's like and, which is a product sort of thing, right? I might like say like a sheaf demands that in all time periods, right? Okay, so we're going to take it of single vertex and single vertex. Well, that's kind of boring. And right? We have only one vertex, and there's no edges to speak of. Okay, let's take it single vertex in a connected pair. Well, look, a single vertex in a connected pair. The vertex doesn't even have a link to itself. And so, we're going to have each pair here. So we're going to have this pair and that one. That's going to be one pair, this and this. Another pair is going to be this and this. And there's going to be no link between them because we would need not only this link going from this side of the pair, and that, but we need a link here from like this to itself, and we don't have that. So we start with something that is actually a connection. We don't have it here. Okay, and here from a connected pair to a connected pair, you might get your hopes up. Well, okay, now we're doing it from one of these to one of these. Okay, we got pairs of, the pairs are like this and this, this and this, this and this, and this and this, right? But look, it's only going to be a morphism, excuse me, not a morphism, an edge, from those pairs if there's one in both. So there's going to be exactly one pair, this and this, and this and this, where there's going to be an edge in both of the constituent sort of pairs. And that's why we only have this thing here. We have four vertices, the two from this times the two for that. Each of these is a pair of one from here and one from there. But there's only one that has the links between it. Even though this has an edge, this has an edge, there's only one because it needs it to be the one on the source end of the pair of things on the source end of each of these guys and the pair on the target end of each of these guys to get that. So you can get the sense of very constructive. It constricts it down. You got to have both or you're going to have none at all in the result. Okay. Let's look at the reciprocal pair. Reciprocal pair is kind of nice because there's ways in each way. But it's still, in this case, it's equal to the coproduct, ain't it? Okay, we gotta keep on moving. Reciprocal pair and connected pair. Well, you might think, well, we're going to get some fancy structure out, but you at least get two out because now you've got some extra flexibility from this guy. You can have it going this way or that way, so you got at least two out. But it's pretty thin gruel. Take a look. Reciprocal pair G end to end. End to end had two end to ends. Again, it's very constrictive. But look, if we have reflexive loops, if we only had a bit of forethought, let's create a connected pair with reflexive loop. Let's take a product of two of these, right? This pair with reflexive loop and this pair with reflexive. Okay, now we're talking. Right? Because we have all these flexibilities. Okay, look, there's going to be four vertices, right? And each pair, if we take this and this, right, this with itself, we're going to have this and this as a vertex, and the result, we're going to have this and this as a vertex, and this and this, and this and this. So it's going to be four. 1, 2, 3, 4. But there's this very nice structure that comes out, right? Where you're going to have like connections between them, and you're not like squeezing them down because you don't have anything to match up. You have plenty of edges to match up, and so you're going to get this very nice structure where we have like this ultimate node where we go like twice through this, or twice this way, or twice that way. And then we have these intermediate nodes, which are kind of formed by, I think, going one way in one, but not the other way, and but not on the other, and then proceeding to that. Rather nice structure, something for you to contemplate. But of course, Catlab can do this all for us. It can compute this all right in front of us. Oops. And to end here, take the product, check this out, end to end with reflexive loops. Okay, by all justice, I should have to graph viz. Let's just check this out here. We should have shown that. There we go. It looks like this, and you take this and you get this very regular structure because we have plenty of these edges to go around to make sure that we're not preventing any matches unnecessarily. And we can go further and do elaborations. So reflexive edges are really important and valuable for like finding things and examining combinations, etc. Okay, I think I'll sort of leave it there for products and coproducts. Coproducts are rather simple structures. Products are simple structures, but just like product of two natural numbers, if one is zero, the product's going to be zero, regardless of how big the other one is. It's going to be zero, right? By building in reflexive arrows with graphs, we can get this extra flexibility and have this, the structure preserved. Okay, I'm going to stop my screen sharing. Any questions before I go on to coproducts and excuse me, push outs and pullbacks? Any questions?